Okay, hey, how's it going? It's 9 o'clock already, and I said I would try to get this video up by 9. Um, so I'll do another one where I do a part one and a part two, so I can get something up by 9:30. So wherever I'm at like 9:20, I'll just cut this off and give you the first 20 minutes. Toward that end, I don't think I'm gonna do number one at all because I think we did pretty much all parts of number one in class. So I'll come back and do them at the end, maybe, but I'm not going to talk about it now. Two, I remember doing that in class too, so I'm not going to do it. I'm mostly going to jump probably to the end of this and do the second one, and I'll come back to all this if you want. All right, so this is maybe a little bit worth doing, so let's do this. Starting with four, so it's fresh in your mind. What is the definition of continuity? We said it had three parts. The first part was about how the function has to at least exist at a. So that means whatever the value of a is, imagine if it's 4, you need to plug 4 into the function and actually get an answer. So f of a is defined, is what we say. Then you need the limit as x approaches a of our function f of x to exist. And that means the left and right hand limits have to both exist and they have to be equal to each other. Then to be continuous, you also need f of a and the limit as x approaches a of f of x. You need them to be equal. And for the next couple problems, it's that third part that's kind of the most important, is we need to come up with a value that makes a given function continuous. And for the function to be continuous, you need your function value to match the limit. So for something like 5, and I'm pretty sure we did do 5 in class, but I'll kind of do it again for everybody. And then maybe I'll find a new one too that's a little different, and I'll give you a chance to try it yourself. You can pause the video, try it yourself, and then work along with me. But the idea again is for us to be continuous. Well, we're already continuous everywhere but -1, because we know this function is continuous everywhere except for the 0 of its denominator. So we're kind of automatically continuous from -infinity to -1 and from -1 to infinity. So the only thing we really have to test is for continuity right at -1. So we would need the limit as we approach -1 of our function to be equal to the value of the function at -1. And again, the limit at -1 only exists if the left and right hand limits are the same. But by the way these intervals are defined, they're saying here that just x can't equal 1. So if I'm coming in from the left, I'm going to use this function to get my limit. And if I'm coming in from the right, I'm still going to use this function to get my limit. So I know that my limit is given by that expression, the x squared plus 3x plus 2 all over x plus 1. And I just want to figure out that guy's limit. Now I need that to be equal to f of -1. Well, when x actually equals -1, we use this expression to find the value. So f of -1 will be the 4c minus 5. So I know I need these guys to be equal. Now if I try to evaluate this limit by just directly substituting in -1, -1, -1, we get 0 in the denominator, and I guess we get 0 in the numerator too, right? Because we would get 1 take away 3 plus 2 all over -1 plus 1. And that's -2 plus 2 is 0, and our denominator is 0. So we're in a bit of a pickle. That, of course, is the indeterminate form. So anytime you get 0 over 0, that's a good indicator that you need to go back to your function and hopefully somehow simplify it algebraically. This is sort of the easy version of what we do. We would take this thing and factor the numerator, and we get x plus 2 and x plus 1. So lo and behold, after just a little bit of factoring, we can get these factors of x plus 1 to cancel out for us. Because once they cancel out and the only thing we have left is the x plus 2, we can substitute into that pretty easily. We would get our -1 plus 2, which gives 1. So we know that that limit is 1. And again, we know that has to equal the 4c minus 5. So if you just kind of bring that down, then by the time you've evaluated that limit, you now have a pretty easy expression on your hands. To solve this, this is an equation by the way, not an expression, but to solve for this, you're just going to add 5, get 6. That now equals 4c. So now just divide by 4, and you get c equals 6/4, which of course reduces down to 3/2. So it turns out that as long as c here is equal to 3/2, then we'll be continuous. Now why is that again? I'm not sure everybody sort of understood that, but if we let c be 3/2, then simplify this. 4 times 3/2 is 12/2. That's 6. 6 minus 5 is 1. And what was our limit up here again? Wasn't it 1? So by letting c be 3/2, then we now are getting a left-hand limit of 1, a right-hand limit of 1, and a function value of 1. And again, that's the literal definition of what it means to be continuous. So that's how you tackle a problem like that. Now for number 6, I had a lot of people get really scared by this problem because it is complicated. It truly is. But I won't give you anything like this, I said what I would give you is, imagine if instead of having all 3 parts, now the fact that we have 3 parts is not actually that bad. The fact that we have 3 parts and we need all 3 is what's bad. So let's just pretend this part wasn't here. And let's pretend that we let x just go all the way to infinity from -2, so I don't need that upper bound. And the fact that I had 2 variables was bad too. Now in class I already did this. Is this harder? Not really. I already did this if you sort of killed the b and solve for a. So you know what? Let's play a little game where we kill the a and we solve for b. So let's solve this. Imagine if you had this equation. What would you do? And the answer is you do the same thing you did before. So, oops-a-daisy. What would we do? We would still find our limit, set it equal to our function value, blah, blah, blah. So to do this one, we know that we need the limit as x approaches -2 from the, well, you know what, let me say it the long way. We need the limit of f of x to be equal to f of -2. But how do I find this limit? If I have to make sure this limit even exists. So I definitely do have to break this down to a left and a right. So I need the limit from the left. I am eventually going to need the limit from the right as well. And where do these things come from? Well, in green, if I want the limit from the left, that's going to come from the x's that are less than -2. So literally this limit just comes from that 6. So it just is 6. On another good note, the value of the function, well, it says -2 is equal up here. So that also is the same 6. So these two guys are already equal. So there's nothing important there. Now, the limit as I approach -2 from the right means I need to be greater than -2. That's clearly the second guy. So that would come from this expression. So that means I could let this whole expression be the x squared minus 3b. And now the fact that I have 6 equals 6, I can kill this. And we can just think about the rest of this equation. Now right now you might be thinking, what do I do with an x and a b? But the answer is x isn't really a variable, because the whole point is we're trying to find the limit as x approaches -2. So we're going to plug -2 in for x, of course. And then the only variable left for us to deal with is this b value. So I'll let that be 6. And at this point, -2 squared will be a positive 4 minus 3b. To solve this equation, you'll subtract 4 from both sides. You'll get 2. 2 is equal to -3b. So I'll divide by -3 and I'll get -2/3. So again, I messed with this problem a little bit differently from how we messed with it before. Before I let the a stay here and we killed the b and solved for a. And we found that a was 9/4, I think. But just to give you a different look at this, our approach is still the same. We still want the limit from the left, the function value, the limit from the right to all be equal. And so the way that shakes out is the limit from the left and the function both just equal 6 from the top expression. The limit from the right is given by this blue expression here. And then you plug in -2 for the x, and you solve for the only variable that's left, which is b, and we're getting that number. So you should certainly expect some question that asks you to solve for some variable to make some function continuous. And hopefully that makes more sense now that you've seen it. Let's move on. So this one, 7, says determine the points of discontinuity, if any. For each point of discontinuity, state the type of discontinuity. If the discontinuity is removable, then state what has to occur for the function to be continuous at the point. All right, so this is this question is similar to quiz 3 that we took, where we had to do all of that. So let's do these, and I guess I'll say both of these here are examples of rational equations, and rational equations are good because we know that rationals are automatically continuous from -infinity all the way to infinity, except for the zeros of their denominator. And usually to find the zeros of the denominator, all you'll have to do is factor. So look in here, I can factor the numerator to get a 2 times x minus 3. And in the denominator, I can factor to get, let's see, it'll be a 2x and an x. Then if I multiply 2 times -15, that's a -30. And we want the factors that add up to -1. So given a 1 and a 30, or a 2 and a 15, or a 3 and a 10, or a 5 and a 6, we're going to go for the 5 and the 6. And if you want a -1, you're going to go ahead and let 6 be negative. And we're going to go with 5 times -6. Now again, remember, we're doing an outer and an inner product. And for our outer product, we already have a factor of 2. So of these two, you'd be going for that 6, and you'd plop a -3 here, so that the -3 multiplies by the 2 to give a -6x. Then you'll let your inner product give 5, so you'll need a +5, so that the 5 times x will give you +5x. And then everything else should sort itself out. The 2x times x is of course 2x squared like we wanted. The +5 times the -3 is the -15 on the end that we wanted. The outer is a -6x, the inner is a 5x, and if you add that up, that's the -x in the middle that we needed. So we know that's the correct factored form. And I'm noticing that these factors of x minus 3 cancel out. Now, even though they cancel out, you still have a discontinuity there. It's just a different kind of discontinuity. It's a removable or a point discontinuity. Now we have another 0 here too, 2x plus 5. If you take 2x plus 5, set it equal to 0, then you can subtract 5 from both sides, you get -5. You can divide by 2, and we see that -5 halves is also a discontinuity for us. So it's what, x equals 3? So I know for a fact that f of x is discontinuous at x equals -5 halves and x equals 3. Furthermore, I can state that f of x has a point discontinuity at the value of x that came from the factor that canceled out. So that's the x equals 3. And the one that didn't cancel out is there'll be a vertical asymptote there, so that's an infinite discontinuity. So that's that. But I still have to, does it say it anywhere? Oh, this last bit, ignore this last sentence. I don't care about that. Don't worry about that at all. So determine the points of discontinuity, done. For each point of discontinuity, state the type of discontinuity, done. You know what it should say up here, of course, and you know it should say it up here, is justify your classification. Classification with limits. All right, so how do you justify the point discontinuity at 3? Yoink. Well, as always, you'll need the limit as x approaches 3 from the left, and you'll need the limit as x approaches 3 from the right. And for a point discontinuity, you'll also need f of 3. Okay, so, well, if point discontinuities come from holes, then the limit as we approach 3 will just be the y value of that hole. And to find the y value, you would normally just plug x into the function and evaluate. But again, if you plug 3 into the original function, you're going to end up getting 6 minus 6, which is 0. And all this quadratic stuff is going to end up being 0, and you're going to be indeterminate. But just don't do that. Remember, we have a simplified formula here. So you can plug into that expression where we've already canceled out. And then you get 2 over 2 times 3 plus 5, which is 2 over 6 plus 5, so 2 elevenths. And of course the limit from the other side will be the same thing. It'll also be 2 elevenths. But if the function value was also 2 elevenths, then we wouldn't have a discontinuity at all. We would be continuous. So you have to tell me that f of 3 is something else besides 2 elevenths. And what f of 3 is it's undefined. If you try to plug f of 3 into the original equation, then you're undefined. So here's your justification of your point discontinuity using limits. You'll tell me that the limit from the left is 2 elevenths, the limit from the right is 2 elevenths. Now because those limits are equal, that means we're getting a point discontinuity, but only if the function is something other than 2 elevenths, and you've shown that too. You've shown that it's undefined. So that's good. Now for the infinite discontinuity, we would do the same basic thing, where again, you better talk to me about the limit as x approaches negative 5 halves, and do it from the left. And also find me the limit as x approaches negative 2 5 halves, from the right. And what you need for an infinite discontinuity is you need both of these limits to exist, and you just need one of them to be infinity. Now, 90% of the time, they'll both be infinity, like positive infinity and negative infinity. But every once in a while, with a piecewise function or something, you might get infinity from one side and then just a constant whole number on the other side. And that's fine. It's still an infinite discontinuity if either one of them is infinity. So what's happening for us? Again, I would urge you to consider the simplified version, the 2 over 2x plus 5. And what I would do if I were you is I would just imagine plugging in a number that's just a little bit less than negative 5 halves. By the way, just a little bit less than negative 5 halves, that's 2.5, right? So imagine plugging in negative 2.6 or something. But if I'm a little less than 5 halves, then doubling it will be a little bit less than negative 5. And then if you try to add 5 to that, you'll be a little bit negative. And 2 divided by a thing that's a little bit negative is going to be a thing that is negative. And that implies that my limit is going to be going down, down, down towards infinity. And I would do the other limit the same way. Just imagine plugging in a number that's a little bit bigger than negative 5 halves. And again, negative 5 halves is what makes us exactly 0. So if I'm a little bit bigger than that, then my denominator will be a little bit bigger than 0. So you'll be getting 2 over something that's a little bit positive. And you'll end up getting a positive, which means your function is going up, up, up towards positive infinity. So again, just keep that straight. Which one is negative? It's simply not true that the limit from the left will always be negative. That is not the case. Sometimes when you come in from the left, you'll get a limit that's going up, up, up. And when you come in from the right, you're getting a limit that goes down, down, down. So you do have to check it. It is important. If you get it backwards, I would mark you down. But there it is. We're doing more than what the paper actually asked you to do, but that's because you know that the quiz will ask you to do all of this. It'll say, where are the discontinuities? Say where they are. Then it'll say classify them, point and infinite. Then it'll also say, make sure to use limits to justify your answers. Okay, that got a little messy, but I hope you understood it. It is 9:22, so I'm just going to stop recording and upload this much at least so it's available for people that want it. And as soon as I do that, I'll go back to work and record more. Bye.